Better not have parvo. Okay, it says we're live. Let's see. We're gonna find out how live we are. Woo! All right. Hello, hello. Hope this series has been serving you well. We are up to the June 2022 test. Yesterday I did the August 2022 test. We're gonna try to speed run this because my dog's got a little bit of a bellyache. We'll see how this goes. We have the test. We have a reference table, calculator, obviously, and we're just going to hop straight into it. No reason to do this slowly. Okay, very first question, part A. We love the part A's because they're reference tables, they're vocabulary. For most tests, you need only 50 questions to pass, and this first 30 is like a really good place to pick up most of those 50 points. All right. The first question, which subatomic particles are matched with their charges? Okay, so we can pretty much bet that the first question is going to be some form of an atomic theory question. And that means that the first question should be very easy to answer. I like to do my tests backwards a little bit. I personally, when I sit down to take a test, that's when I'm like amped up and ready to go. So I like to start at the end of the test, which is typically like your tougher answers or your tougher questions rather. And then, because these questions are so easy, other people need like the little confidence boost that comes with getting a very easy question to start with. So we know that protons are positive, neutrons are neutral. So it can't be this one. Protons are positive, electrons are negative. That is the answer. Protons are positive and electrons are negative. Yes, protons are negative. Nope, protons are negative. Nope. Okay. Place on the reference table you could have found that was, let's clear all of my annotations from yesterday. Yes, delete them. Delete. You could have found all of that on table. Oh, this is a positive one right there on the proton. Neutron is 0 for neutral. The electron, not labeled, but it's labeled as a beta particle, negative. Moving on to number 2, the gold foil experiment. Okay, we know Rutherford has the sheet of gold foil. He's launching alpha particles at the gold foil. Most of those alpha particles go straight through the foil and hit the back of the detecting screen, upwards of 99%. That told him that the atom is mostly empty space with a small, dense, positive nucleus. So the answer that applies here is answer 1. Atoms are hard, indivisible spheres was Dalton. Electrons are located in shells. This like shell/orbital thing, that's Bohr. And atoms have a very small mass. They kind of figured that one out from the jump. That would be even before Dalton. That would be Democritus way back when. Bright line spectrum. I love it. The bright line spectrum of an element is produced when excited state electrons release energy and move to lower energy states. So we have an atom. Let's say it's an atom of, I don't know, carbon. So we got 6 protons. We have 2 layers of electrons because carbon's in period 2 / the electron configuration has 2 digits. We have 2 electrons in that shell right there, and then we have 4 right here. Obviously, I've only drawn like half of this. So what happens is we heat up this carbon, and these electrons go, that's hot, and they jump up to higher energy levels. And this is because they have absorbed the heat energy from a flame, or they have absorbed electrical energy from getting zapped. Like in a neon light, you provide electricity. They jump up because they have absorbed energy. The nucleus is positive, right? Electrons are negative. Eventually, the electrons are going to be called back towards the nucleus by charge attraction. Also, they can't maintain the energy needed to overcome that charge attraction. So when they fall back down to ground state where they belong, they fall to lower energy levels or energy states. They have to release that energy that they had originally absorbed. And then when that comes out, we're going to get the colored light, which you would have seen in a flame test. And then the spectral lines are when you read the information from that, green, blue, purple, red light, whatever it is. Number 4, the elements on the periodic table of elements are arranged in order of increasing atomic number. It used to be atomic mass, and that is how Mendeleev originally organized the periodic table. Mass number is not on the periodic table. An oxidation state, you can look at the periodic table. It kind of increases, but then it decreases. So that answer choice doesn't really make a lot of sense. Okay, so the atomic number is this one right here. So in carbon, it is 6, but in, let's say, no one cares. When it's lithium, it's 3. When it's beryllium, it's 4. When it's boron, it's 5. And we read from left to right, so obviously this is organized by increasing atomic number. The oxidation state, you can see, like, if you look at period 4, we have +1, +2, +3, plus a bunch of numbers, plus a bunch of numbers, plus a bunch of numbers. And then you kind of like go back to 2, 3, +3, and then you hit a bunch of negatives when you hit arsenic over here. So oxidation state is not a proper answer. And then mass number doesn't go on here. It's not on the periodic table. If you take the mass and round it to a whole number, that gives you the mass number, which is the protons plus the neutrons, but it's not on there by itself. Atoms of which element in group 15 have the greatest electronegativity? I know the answer without even looking at table S because I'm using my periodic table trends. We have arsenic, nitrogen, bismuth, and phosphorus. I feel like I've had a question very similar, or had the exact same answer choices recently. Yeah, I think the question was like, which of these is a metal? Nitrogen, phosphorus, arsenic, or bismuth, which has the highest electronegativity was the question. The answer is going to be nitrogen, and that is because it's the closest to fluorine. Fluorine has the highest electronegativity at 4.0. Nitrogen is the closest, so it'll have the highest electronegativity. They're in the same period. You could also go and look those all up on table S, which follows right here, electronegativity values. We were talking about nitrogen, phosphorus. You see it's decreasing. What was the next one? Arsenic. 2.2. Oh, that one actually stayed the same between phosphorus and arsenic. And then we had to scroll all the way to bismuth, which is like 80 something right here. And that electronegativity is 1.9. So the periodic table trends were correct, but considering it's a part A question, you can go and look them up. No one says that you can't. Okay. Number 6. Which term represents the simplest whole number ratio of atoms of the elements in a compound? This is a vocabulary question. The simplest whole number ratio of atoms of an element is the definition, and they're asking for the term that matches that definition, and that term would be the empirical formula. If we had C6H12O6, that's glucose. That right there is a molecular formula, the actual real-life formula of the substance. But the empirical formula, I don't want to draw this like it looks like a chemical reaction, so I'm going to put 2 arrowheads on it. The empirical formula would be the most reduced version of that. So 6, 12, and 6 are all divisible by 6. For every 1 carbon, there's 2 hydrogens and 1 oxygen. That's what the empirical formula is. The atomic mass is the sum of all of the elements, or all of the atoms. No, this is the sum of all the masses of all the atoms. The formula mass is the same thing, and structural formula is like a Lewis structure when you draw it. Love number 7. How many electrons are shared in a triple bond? Doesn't really matter, but you should know that nitrogen is the element that loves to triple bond to itself as a diatomic. And its Lewis structure looks like this. And what happens is that we'll do the purple. This purple nitrogen on the left has 1, 2, 3, 4, 5 valence electrons. It puts 3 into that bond. And then this orange nitrogen on the right, 1, 2, 3, 4, 5, also has 5 valence electrons. The nitrogens say to each other, I'll share 3 with you if you share 3 with me. That's where the triple comes in. So they share 3 each, but the total number of electrons in a triple bond is 6. 3 from each atom. Number 8 is one of my favorite questions because it's just an acronym. This is BARF. And I'm sorry if that upset you, but that is the best way to remember this. BARF. When bonds are broken, energy has to be absorbed. We'll just say absorbed for the sake of space. And then when bonds are formed, or rather energy is released when bonds are formed. So that's BARF, BARF. We are looking at diatomic chlorine breaking apart into 2 chlorine atoms. And because we are breaking right here, it's the BA in BARF, we are absorbing energy. So energy is absorbed and a bond is broken. Okay, moving on to number 9. Krypton atoms in the ground state tend not to bond with other atoms because they're blank. Okay, let's take a look at krypton. Krypton's number 36? Yes, it is. Okay. We have krypton right here. The question was asking about electrons. So its configuration down here across the bottom is 2, 8, 18, 8. I'm just going to carry that over to the question so we can take a look at them together. 2, 8, 18, and 8. Okay, so the second energy shell, the second electron shell has 8 electrons. The third contains 18. The innermost contains 2, and the outermost contains 8. All of those are factually correct. The question is, which one is the reason why krypton does not bond with other atoms? And all of chemistry, all of it, except for nuclear, is based on electrons, and specifically, it is based on valence electrons. When in doubt, the answer is going to be valence electrons. We are talking valence electrons specifically are the outermost electrons. And the fact that krypton has 8 in that valence shell means that it is content. It doesn't want to bond anymore. That's the octet rule. If you were going to make sure that you knew your vocab terms, this is the octet rule. Atoms that are bigger than helium and lithium, bigger than lithium, want to have 8 valence electrons. I should say bigger than beryllium. Big atoms want to have 8 valence electrons so that they look like the noble gases. They would have 8 in the valence shell because that makes them extra stable. Okay, all matter can be classified as an element. No. Water is not an element. A compound? No. Gold is not an element. A mixture or an element? No. Water is not a mixture, nor is it an element. It must be a mixture or a substance. This, again, is vocabulary. Mixtures are going to be your homogeneous or heterogeneous mixtures. And then substances, sounds like it's like a super general term, but it really means element or compound. So again, another vocab question, which we absolutely love to see in the part A. If there are any questions, feel free to ask them in the chat box. Otherwise, I'm going to keep moving and grooving. Okay, number 11, which sample at STP has the same chemical properties as 10 grams of aluminum solid at STP? We're talking specifically chemical properties. So chemical properties are going to describe the way that a substance does or does not react. So in the case of aluminum, it would be like it'll oxidize in air. It will react with metals to form hydrogen gas. Not that it's shiny, not that it's silver colored. Those are physical properties. So if you're talking about the way something looks, feels, smells, or something about the size of it, like its mass, its volume, those are physical properties. Chemical properties are things that you would have to learn by doing. Okay, not learn by looking, learn by doing. So the only way you would know that aluminum oxidizes is if you expose it to oxygen. The only way you would know aluminum reacts with metal is if, or rather reacts with acid, is if you put it in the presence of acid. Okay, so we're going to take a look, and this is going to be the 5 grams of aluminum. They're going to have the same chemical properties because they're made of the same atoms. And that would be that. They're going to have like different sized reactions because the aluminum at 10 grams is larger than the one at 5 grams. But otherwise, their actions should be the same. Number 12 is another vocabulary question. Which sample of matter cannot be broken down by a chemical change? That is the definition of an element. But then you have to take that and apply it to one of these terms. So we have antimony, ethanol, methane, and water. We are specifically looking for an element, which means that you would find it on the periodic table of elements. And if you don't know what something is in terms of elements, remember you can look it up on table S. We have names. And if you really don't know what antimony is, then you'd be looking for a while because it's number 51. There's your element, antimony. It has a weird symbol. It's SB, which is maybe why if your teacher had you memorize symbols, antimony was not chosen. It doesn't come up very often, but it is a metalloid, which is why I have always made my students learn it because there's not that many metalloids. So it is antimony. Ethanol, even by process of elimination. Ethanol, you should know, is a carbon compound. Methane, you know, is a carbon compound. And water, you know, is H2O. So at that point, you should have had the idea, hey, this is antimony. And then maybe you double-checked it on table S. All right, 13 is based on table F. Which 10-gram sample, when thoroughly mixed with 1 liter of water at room temperature, forms a heterogeneous mixture? Okay, this specifically means that you are looking for something that is saturated. And it's telling us specifically to look at table F. Saturated solutions, or rather heterogeneous solutions, means that you are going to have liquid and you're going to have some solid sitting on the bottom. And for some reason, this thing doesn't want to dissolve. You are only taking 10 grams of this and dissolving it in 1 liter of water, which typically means that this thing that you're talking about is insoluble. So we're going to go take a look at table F. Table F used to be one of my least favorite tables, but it has become one of my most favorite tables because I figured out the perfect way to read it. Reading table F is not that much of a nightmare if you consider, I'm going to make my line nice and bold here. If you circle these inner 2 columns, Sorry, this tablet is not my favorite. If you've been here, you know that the aspect ratio of this tablet does not match the screen, so it's too small. This right here, those inner two columns are going to represent insoluble compounds. So if you have a compound whose ions make the thing fall into the circle, then your substance will be insoluble. So we were looking at, let's see, ammonium chloride, NH4Cl. Ammonium is right here, and it loves to dissolve no matter what it's bonded to. That's why the exceptions are blank. So ammonium is going to dissolve. It'll basically never give you a heterogeneous solution. Potassium iodide, Ki, is a group 1 ion. Potassium, K, is in group 1. It dissolves all the time with no exceptions. So that wouldn't give us a heterogeneous solution. Then we have silver bromide, AgBr. Silver bromide, silver doesn't have anything that's gonna like categorize it, because when we use table F, you have to look at this column or this column, because those are the rules, and then we have exceptions. So silver isn't in column 1 or in column 2, or rather 3, but bromine is. Bromine is part of the halides right there. Bromine would typically like to dissolve, but silver specifically says, no, we're not dissolving. We're going to stick together. So silver bromide will give us the heterogeneous mixture there. And then finally, we have the sodium nitrate, NaNO3. Sodium is a group 1 ion. It always dissolves with no exceptions, and the same is true for nitrate. Always dissolves, no exceptions. So that gives us silver bromide. Okay, 14. Compared to a 1 molar sodium chloride solution at 1 atmosphere, a 2 molar sodium chloride solution at 1 atmosphere has, each of these are going to display colligative properties, which really is just a change in physical properties of water based on something being dissolved in that water. And for high school students, I think the best way to describe it is that we have a thermometer. We have a thermometer, and typically the freezing point of water or the melting point of water would be 0 Celsius, and the boiling point would be 100 Celsius. When you add salt to the water, your boiling point is going to rise. Let's say it goes up to like 105, and the freezing point is going to drop, and that's going to take us down to like -5 Celsius. Okay. When this happens, from this point up is a solid, and then from, or not a solid, that would be a gas. That's a gas. And then from this point down would be a solid. So that means that everything in the middle here is liquid. So truthfully, what has happened is that you have expanded the liquid phase. The boiling point goes up and the freezing point goes down. And when you expand the liquid phase, that is going to be based on the number of particles in the solution. So there's 2 ways that you can increase the number of particles. Number 1, which is shown here, is to increase the molarity. You just shovel in more solute. The second way is that you would have a solute that breaks into more ions. So we have NaCl here, but if we had MgCl2, this would break apart into an Mg, a Cl, and then a second Cl. So that's going to give us 3 particles. So again, the 2 ways to expand the liquid phase of water is to increase the concentration or change the substance so that you have more ions coming out. So here we would have a higher boiling point and a lower freezing point. Wait. Yes. I'm just making sure they didn't flip-flop the things on me. 15, we're looking for 3 forms of energy I bet you the number one wrong answer is number one. Temperature is not the same thing. Well, what is electromagnetic energy? I think it's 3. I think they want the answer to be 3. Hold up. Now I want to go take a look at this. Because temperature is average kinetic energy. Chemical energy is stored in bonds, and then thermal is like the Q equals MC delta T. But like electromagnetic energy is like not really a thing, but it's kind of a thing. I would make an argument that gamma rays are a form of electromagnetic energy. It's obviously not 2 or 4 because alkalinity is like an adjective describing how basic something is. Where is the multiple choice key? Scoring key. There we go. They are saying... Can I not zoom in on this? Question 15, they want it to be 3. Okay. I don't love this question. Honestly, this is something that I maybe would have written to the Regents Board to contest. Because I don't like the whole electromagnetic thing. I mean, that's the thing. Regents Chem, we don't really talk about like the electromagnetic spectrum. It's not part of our standards, which is another reason why I don't love this answer choice. Yeah, really just like not feeling it. But that's okay. It is what it is. We just rock and roll. And there we have it. Obviously not alkalinity, so we could rule out those. This one is average kinetic energy. Chemical is stored in bonds, and then thermal is Q. So that's how I would have figured that one out. Okay, 16 says, under which conditions of pressure and temperature is a real gas most like an ideal gas? And that is going to be under conditions of plight, which is an acronym. It's pressure low, ideal gas, high temperature. And that is PLIGHT. Plight is going to tell us when we have an ideal gas. Ideal gases occur when the pressure is low and the temperature is high. And really what this means, there's a whole video on it on this channel. The kinetic molecular theory describes how gases behave and says that they don't have intermolecular forces. There's no attractive or repulsive forces in gases, in ideal gases. That is going to be the most likely case when we have a low pressure because we're not squeezing the molecules together, and when we have a high temperature because they're moving around really, really fast and they're like whoosh, whizzing past each other that they don't get a chance to feel IMFs. Question 17. Which sample of argon gas has the same number of atoms as a 100 milliliter sample of helium gas at 1 atmosphere and 300 Kelvin? For this one, you may be thinking that you need to do some math because it's giving you a lot of numbers. You don't have to do math because it's a part A. You also don't have to do math because this is an Avogadro's law question. For our purposes, Avogadro's law we only do in concept. We don't actually do the calculations for Avogadro's law. Avogadro's law is basically saying if you have 2 gases and they are at the same temperature and pressure, and you have the same volume of those 2 gases, then you have the same number of particles. Because if it's the same, then it's the same. That's what Avogadro gets credit for saying. If it's the same, it's the same. And what that boils down to is that gases on their own don't really have a unique identity. Little hydrogen molecules in the gas phase are going to, like in a non-reacting situation, are going to behave exactly the same way as carbon dioxide molecules, and they're going to react or act the same way as helium atoms, so long as they're not undergoing a chemical reaction. Because if it's the same, then it's the same. So we are looking for a 100 milliliter sample at 1 atmosphere of pressure and 300 Kelvin, because if it's the same, then it's the same. Question 18, which is a chemical change. In order to have a chemical change, you have to have bonds broken or bonds being formed. And phase changes are not chemical changes. Again, phase changes are not chemical changes. All they do is take molecules or atoms and pull them apart from each other or squeeze them together. It's more so related to intermolecular forces. The synthesis is a formation. So you'd have magnesium element and oxygen element coming together to make magnesium oxide. So it would actually be Mg plus O2 makes MgO. And then you have to put a 2 right there, and you have to put a 2 right there to balance it. And that would be your synthesis. Question 19. Which property is determined by the structure, arrangement, and interactions of the molecules of a substance at a given temperature and pressure? Specifically here, we're talking arrangement of molecules at a given temperature and pressure. This is their physical state, or their physical state of matter, or their phase of matter. Atomic radius is not going to change based on temperature or pressure. Half-life, not happen. And then formula mass. Ooh, that's not happening either. The only way to change formula mass is for something to undergo a reaction and then become something else. Question 20. A collision between reactant particles is most likely to result in a reaction when the particles have proper orientation and proper energy. That is, again, a beautiful definition, and the definition is of effective collision. So if you have particles, let's color this one in and this guy, and then we do, I don't know, this and this, they're not going to react because we may get these like green ones to react with each other, but the two white are not close enough to have a reaction. So that is not going to be effective. What would be effective would be to like color it in and then they go like snowmen side by side. And then that would give us like the double, well, actually they'd look like this. They'd go sideways because they're reacting towards each other. So that's proper orientation, but the proper energy means that they can't just like casually be like, hey, want to react? They have to be like, do you want to react with me? And then they, boom, smack into each other real hard. They're passionate. Number 21. Given the equation representing a system in equilibrium, which statement describes this reaction at equilibrium? Guess what? This question is, what is the definition of equilibrium? It's so like annoying how they rephrase all of these to make them sound like really complex, but simply it's just asking you what's the definition of equilibrium here. Very annoying. So the rates in equilibrium must be equal. The rate of going to the left has to be equal to the rate going to the right. The forward is equal to the reverse. So if they are equal, what would happen is that your concentrations would remain constant. Let's just say for whatever reason, I am in a 10-liter container, and here I'm working with I don't know, 6 liters of NO2 and 3 liters of N2O4. That doesn't add up to 10. Okay, I'm in a 9-liter container. If these two arrows are equal, my rates are equal, then this 6 won't change and that 3 won't change. Those two numbers don't have to be equal to each other. If you need to see that in action, I did a lab on this channel with the water going back and forth in the graduated cylinders, so you can see that to see it like actually happen. No reaction there. You could also do the same thing with like measuring cups in your own kitchen. So the rate of the forward and the rate of the reverse are equal. So neither of those work. The concentrations must be constant. Here we go. 22. Which phrase describes the effect of adding a catalyst to a chemical reaction in order to increase the reaction rate? It is number 1. It's kind of like just the definition of a catalyst. It's going to provide a different or an alternate reaction pathway is what they like to use a lot. That's fancy science for it gives the reaction a shortcut, and with that shortcut, it's going to take less energy for the reaction to start off. So that activation energy is going to decrease. It makes it easier. 23. This question I think is like on every single test. Systems in nature tend to undergo changes toward, and that is going to be low energy and great disorder, or a high entropy. You would relate this to like you cleaning your room or not putting things in the hamper, not putting your shoes away in the closet, putting your dishes in the sink instead of putting them in the dishwasher. You're going to do the lazy thing, and the lazy thing is going to make your life messy. And that's just because you are a part of nature the same way I am. I have a pile of clothes in my background that need to be put away. And that's just laziness, because we're part of nature. Nature is lazy and messy, just like you and me. 24. Which element must be present in an organic compound? I hope that you know that that's carbon. On the reference tables, we would see a little bit of that. Right here, organic prefixes related to carbon atoms. Just in case your brain just melts in the middle of the test. Because mine does. You should see how I am at the end of the stream compared to the beginning of the stream. Okay, 25. Which formula represents a saturated hydrocarbon? A saturated hydrocarbon would, by definition, be an alkane. So again, they're using vocabulary here to kind of figure out if you know what chemistry is. Part A is a vocabulary test. It's an applied vocabulary test. Saturated hydrocarbons are alkanes, and alkanes follow this formula here. Alkanes, remember, are carbon chains that have only single bonds. If that's true, then we take the number of carbons, and in order to find out the number of hydrogens, we would double it and add 2. So that would be this one right here. If we have 6 carbons, if we double it, we would get 12, add 2, that's 14, and that gives us the 14 hydrogens. And that would be hexane, because it has 6 carbons. C2H2 would be triple bonded. That would have to be an alkyne. C2H4 would be an alkene, because it has to have a double bond. Don't believe me, draw it. And C6H10. 2 double bonds in there, I think. I'm not drawing it. We're just going to say there's 2 double bonds in there. You can draw it and tell me. It's not the right answer. We're not spending time with it. 26. What reaction occurs at the anode of an electrochemical cell? Pretty sure we had this question on the last test that we did, possibly with different answer choices. So what I was saying for that question is that you know by reading this question that we're talking about redox. An electrochemical cell, if you've been paying attention, you know that that's a redox question. So if it's a redox question, then your answer is probably a redox answer. Saponification is the organic reaction for making soap. Esterification is the organic reaction for making an ester. I have a thunderstorm rolling in. I don't know if you can hear it. That's the wind rustling the leaves. Holy moly. Oxidation and reduction are obviously the only two answers that are left over. The way to remember this is that acronym ANOX. And red cat. ANOX helps you to remember that oxidation occurs at the anode, and red cat is that reduction occurs at the cathode of an electrochemical cell. So for this, the anode, we're choosing oxidation. '27. Which statement describes the two types of reactions that occur in operating electrochemical cells? Okay. I hate when they do this. It's two answers but one question. Okay. Voltaic cells happen on their own. That is just by the, quote, magic of chemistry. When you connect two metals, metals are just trying to lose electrons. And whichever one is, quote, the more powerful metal or higher up on table J is going to push its electrons through the wire and send them over to that other metal. And that is a spontaneous thing when the metals are in contact with each other. So that is spontaneous in the voltaic cell, but it's non-spontaneous in the electrolytic cell. The electrolytic cell requires energy. So either it'll be plugged into an outlet or it is going to require a battery. Kind of a lot of vocabulary mixed up in there. 28, they will never flat out say Bronsted-Lowry acid-base theory. I don't know why. An acid, according to the Bronsted-Lowry acid-base theory, is a donor. So this BAD stands for bases accept, acids donate, and specifically there we're talking about H+, which is also called a proton. It's hydrogen after it's ditched its electron, which at that rate would just be a proton left over. So bases are going to donate. They donate their H+, and they give it to the base who accepts it. 29. Which emission will be released from an unstable iron 53 nucleus? This one is a straight up reference table question. I would never be able to answer this without a reference table because it's not like a relevant thing that comes up on the regular. We are looking for iron 53, which their symbols go in alphabetical order. Not their names. So here we have Fe53 and it's B+, but B+ is not an answer choice here. So we can go cross-reference that B+ with, where is it? This reference table here, B+, or this B+ is the positron, which I hope you knew, but if you didn't, is on the reference table for you. Positron. Okay, number 30. What is the potential risk associated with radioactive isotopes? Okay, risk is going to indicate that we're talking about a bad thing. Curing of diseases is definitely a good thing, so that's not going to make any sense. Tracing chemical processes, I would argue, is a good thing. Industrial measurements, I would argue, is a good thing. Something that's definitely a risk is biological exposure. We know that radioactive isotopes can cause like cellular damage, and if you have enough cellular damage and your body doesn't work to fix it, then you can get like different types of cancers and other diseases. So radioisotopes can be really good if they're used strategically, but just like haphazardly thrown around, too casual, not good for us. Okay, now we're up to part B1. B1 is going to be like your pretty straightforward questions. B2 is where they kind of step up, and then C is where they're going to apply to stuff. So we are really going to try to get through this because I need to feed the DOG in 45 minutes. So let's see if we can do this. 31. Which electron configuration represents the electrons of a phosphorus atom in an excited state? The first thing to do would be to find the ground state configuration of a phosphorus. And, oh, you know what I can do? I can do that. No, don't do that. That's not what I asked for. Ah! Thank you for being patient with me. I appreciate you. I'm good, but not that good. Okay, back over here. Slide this. There we go. Phosphorus is P. Ugh. And it is right here. They've asked quite a few questions about phosphorus at this point. The configuration is 285. That's the ground state configuration. Oops. 285. So that cannot be the excited state. That's the ground state. Next off is that phosphorus has 15 electrons. So my only answer choices are those that include 15 electrons. So here, no, and here, no, right? Yeah, this one's just adding an electron. This is subtracting 2. This is what happens. It is actually choice 3. The electron from level 2 jumps up to level 3, so you would subtract 1 from there, but add it back in the third level. So it would become 2, 7, 6. (32) A 26.7 gram sample of which element has a volume of 3 cubic centimeters at room temperature? Blah. This is density. Density is mass divided by volume, and it is a physical property, so we can use it to distinguish elements from each other, sometimes even substances. So what I'm going to do is plug in the mass, 26.7, divide that by the volume of 3 cubic centimeters. The density that I am getting is 8.9 grams per milliliter, or grams per cubic centimeter. That's the same thing, because 1 milliliter takes up a cubic centimeter of space. And then what I will do is cross-reference this with table S to figure out what we are talking about. So chromium is 30-something, 20-something. Chromium's density is 7.15. It must be raining somewhere nearby because I'm telling you, my emergency response people are always out when raindrops hit the ground, and I can hear them in the distance. Cadmium is 50-something. Cadmium right here. Density is 8.69. Then I have NB. What's that? Niobium? I don't know where niobium is. There it is. Number 41. The density there is 8.57. And then nickel is with the transition metals in that first row. And its density is exactly 8.90. So that is our answer. 33. Which element is a nonmetal and a solid at STP? So lead, you should know, is a metal. And sodium, you should know, is a metal. And nitrogen and sulfur are nonmetals, but nitrogen is a gas. It makes up almost 80% of our atmosphere. And sulfur is that smelly yellow, like chalky rock from earth science. 34 asks, what is the molecular formula of CH3CH2COOCH3? And we're just going to count them up. So I have 1, 2, 3, 4 carbons. So I'm looking for C4. H is next. That's 3 plus 2 is 5 plus another 3 is 8. And then I have 2 oxygens right there. So that'll give me O2. And that would be it. The molecular formula is the real true life formula of a specific compound, not to be confused with the empirical formula, which is the just the ratio of elements, one to the next. 35 also could have been a part A question. A substance conducts electricity in the liquid phase, but not in the solid phase. That is something that would have to be ionic. Covalent does not conduct at all. Metallic would conduct in the solid phase. Covalent and molecular are the same thing. Covalent substances technically are not correct. It's actually a molecular substance has covalent bonds. But ionic stuff, it will conduct if it is dissolved in water, i.e. aqueous, or if it is molten, which is what we say for ionic stuff because it's so hot that it's like lava hot. 36, a student measured the melting point of a sample of gallium to be 309 Kelvin. Based on table S, which numerical setup can be used to calculate the student's percent error? Okay. We need the melting point of gallium in Kelvin in order to do this. Gallium is Ga. It's right here. And the melting point is that first thing. It's 303. So we are looking for measured minus accepted over accepted times 100. That's on table T. If you forgot, that is the last table on the reference table. I know it's sideways, but the percent error is right there. Measured value minus accepted divided by accepted, and minus A over A. So the student is measuring 309, and the accepted was 303, and we have to multiply that by 100 in order to turn it into a percent. So that's going to be choice 1. No. Yes, it is. 303 was the accepted. Sorry. 37, which chemical bond is most polar? Oh, interesting. Okay, so we're talking about bonds, so it literally, like, this part of every single choice does not matter. Is it O bonded to H, S bonded to H, SE bonded to H, or TE bonded to H? To figure out if a bond is polar, you would do the bond electronegativity difference. You look up the electronegativities and subtract them. But I also know that on the periodic table, we have oxygen, and then sulfur, and then selenium, and then tellurium. And the things with the higher electronegativity are at the top of the periodic table. So knowing this, I know right off the bat that this one, this oxygen hydrogen, is going to be the most polar because the hydrogen is not really changing, right? It's going to be 2.2 for each of them. And if oxygen is the highest and tellurium's the lowest, obviously that's going to make us the most polar bond. And you could look up each of these on table S if you didn't want to pull in the periodic table trend. 38. What is the amount of heat required to melt 43 grams of solid magnesium at its melting point? And then it gives you the heat of fusion. Okay. They have to give you the heat of fusion specifically because they're asking you about magnesium, and the reference tables will only give you the heat of fusion for water. So you can't use reference tables for this. Aside from the formula, I guess. You would use the formula Q equals MHF. And then all you have to do is multiply the mass times that 1.9 times 10 to the third. And that's all. Your answer should come out in scientific notation based on the answer choices. 1.9 E3. Okay, so the answer choice that I'm getting is 81700. And in the calculator, I'm working on the TI 30. Probably whatever standard you're going to get. You can hit second and then DRG right next to it. Slide over to SCI. It'll automatically put that in scientific notation for you. But then you have to get it back out of scientific notation, so do the same thing, but reverse. Truthfully, what's going to happen, you have a decimal point back here. You'll move it 1, 2, 3, 4 times in order to get it between the 8 and the 1. So that means your exponent is 4. So it's 8.2 times 10 to the 4th. There is 2 videos on this channel on converting scientific notation. So if you need help with that, go there. I'm not spending time on it. Given the diagram of a lab apparatus, this apparatus is used for which process? This is for distillation. We're working with a hot plate there, so obviously we need some heat. We are condensing stuff, so we're doing a phase change. That is distillation. For a filtration, you're going to use like a funnel and a piece of filter paper. Chromatography often is like the beaker and a water level and then a little strip of paper that's going to have like an ink dot on it, or it'll have like pigment from a plant. And then electrolysis is typically going to be an electrolytic cell. Question 40. Solid aluminum has a specific heat capacity of 0.90 joules per gram Kelvin. How many joules of heat are absorbed to raise the temperature of 24.0 grams of aluminum from 300 Kelvin to 350 Kelvin? Q equals MC delta T. That is on table T of the reference tables. You go there anytime you have to do math. It's the only table for math problems. Q is based on the reference tables, the amount of heat, which is what we're looking for. It asks us how many joules of heat. So I'm going to leave Q. The mass here is 24. C, according to the reference table on table T, is the specific heat capacity, and it gives us its 0.90. And then delta T is the change in temperature. So the change in temperature, it went from 300 to 350. So we would be multiplying all of this by 50 because that's how much the temperature rose. So 24 times 0.90 times 50 is giving us, I'm still in scientific notation, 1080. 1080 is going to round to 1100 based on the rules for sig figs, because I only need to, well, I can only have 2 sig figs. So it would be 1100. Oof, okay, based on table G, which solute sample in 100 grams of water at 40 Celsius can produce a solution equilibrium in a closed system? Solution equilibrium is telling us that the solution is saturated. So again, vocabulary, very pertinent here. We are looking for a saturated solution. And we can take a look at table G, which is very nice of them to tell us it's table G. Oh, see right here? Q equals MC delta T. It tells you what everything stands for. Very nice, right? I hate table G because it's a disaster. Speaking of reference tables, I did a live stream earlier this week on what the tricks are for each reference table. So if you need help with that, definitely go watch that stream. we here are looking at different solutions. We're looking at 40 degrees Celsius. Oh, I hate when they do different masses. Okay, so I'm going to do these in different colors. 10 grams of KClO3 at 40. 10 grams of KClO3 at 40. I'm just going to label that as 1 because it corresponds to answer choice 1. 25 grams of NaCl at 40 would be right here. That's answer choice 2. Number 3 is 45 grams at 40 degrees Celsius. So that's choice 3. And then choice 4 would be 55 grams. And that is choice 4. Okay. The question is, which of these is going to give me a saturated solution or have a solution equilibrium? For a saturated solution, it means that one of those data points is above that particular substance's line on the table. So, for example, is the dot labeled 1 higher than the line for KClO3? And no, it's not. The line for KClO3 is right here. And data point 1 is beneath that line. So that would be unsaturated, therefore not the correct answer. 25 grams of NaCl. The line for NaCl is right here. And 2 is below that. So that's going to be unsaturated. Whoop. KCl is right here. And choice 3 is, that was the ugliest line ever. Choice 3 is above that. So that's the answer. But I still want to check on the other one just to be sure because table G, man, confusing. I don't like it. And then finally, 55 grams of KNO3. The line for KNO3 is this one here. And data point 4 comes beneath that line. So that's also unsaturated. Now, they haven't given us one of these yet. This is the first one. I call it the Sesame Street question because really the answer is going to come down to which one of these is not like the others. 3 of the data points come below the line. 1 of them is above. It's going to be the one that's above. 42. Given the equation representing a system at equilibrium, which change favors the forward reaction? Okay, let's find out. If we increase the concentration of oxygen, that would correspond with add away. So if we bump up a bunch of oxygen, then we would have to use it up. And we would create a bunch of this SO3. So I like this one, but I'm going to check on the others just to be sure. Increasing the temperature. This reaction, as it is written, is exothermic. The energy is coming out, and I know that because the energy is a product, meaning this reaction is releasing a bunch of energy. If I give the reaction a bunch of energy, it says, wait, what are you doing? I'm trying to get rid of this energy. So that's going to make the reaction go backwards. Decreasing the pressure. Pressure's a little bit weird because it is based on the number of moles of gas, and it'll only work if the system is all gas. If we decrease the pressure, the reaction is going to shift to the side with more moles of gas to get that comfortable pressure back. So that, in this case, would shift us over to the left because here we have 2 moles of gas and 1 mole of gas. Nothing written there, but it's a 1. So that won't work. If we decrease the concentration of SO2, the SO3 is going to break apart to make more of the SO2, and that'll send the reaction backwards as well. So this is going to be choice 1. (43). I love it. This is entropy, and it's really just like an applied vocabulary question. When ice melts at 0 Celsius, entropy increases because blank. Entropy is related to how organized the particles are. It's connected to temperature, but not like explicitly connected to temperature. If something's hotter, then obviously it's going to have more disorder than the same thing that's colder. But as ice is melting, the temperature is not changing. So this in other circumstances would be true. If you increase the temperature, entropy will increase, but we're not actually increasing the temperature. And we're not decreasing it either. It's in the process of melting, so the temperature is remaining the same. Particles are going to become more random. That is the correct answer. When we melt, we're going from solid to liquid. And as that happens, your particles are like making a puddle. They're getting less organized. This was a free response question. These tests are so repetitive. At STP, propanal and propanone have different chemical properties due to their different structures. Properties are always going to come down to structure. Propanal and propanone, if you were to draw them, they're isomers of each other. And we kind of did this yesterday in that test. Propanal is going to have 3 carbons. The Al at the end tells you that you have a double bonded oxygen on the end of the molecule, but propanone is going to put that double bonded oxygen in the middle of the molecule. It just can't be on the end, and in propanone, the only option is the middle. And then fill in the rest with hydrogens. They are identical. So they're going to have the same molecular mass because they're made of the same stuff. They're going to have the same empirical formulas because they reduce to the same numbers, whatever they may be. Well, actually, their moleculars are the same as their empiricals because they only have 1 oxygen. And then their percent compositions, because their isomers, have to be the same. So it's going to come down to the functional groups. Really what happens is that the propanal with the oxygen on the end is going to be a touch more polar than the one in the middle, because the one on the end, the electron cloud, is like more exposed to other molecules. Okay. Right here, what is the IUPAC name? Okay, we have to find the longest carbon chain, which I am seeing as 1, 2, 3, 4, 5, 6 going straight across or 6 going down. Either way is fine. And then I have a 1 carbon dangle right there, and I have a 1 carbon dangle right here. So considering I have 6 in a row, that is the base of that is going to be, or rather the main chain is going to be a hexane, because hex is the prefix for 6. Right? Hex for 6, ane because it's all single bonds. And then the question is it 2,3 dimethyl or is it 4, 5 dimethyl? And we want our numbers to be the lowest possible. The way that we figured this out is that we number the molecule both forwards and backwards, because in real life, these molecules are moving around and twisting and whatever, and there's no guarantee that you and I are looking at the same side of the molecule. Like if it were a hand, you might be looking at the knuckles while I look at the palm, but then if we spin it around, you know what I mean? We want the thumb to be at the same spot. So we number it in both directions to make sure we're looking at it correctly. The purple is going to be the correct answer. This is a 2-methyl, and that's a 3-methyl, and because I have 2 methyls in total, that gives us the di in the methyl. 2,3-dimethylhexane. Moving right along. The organic functional group, I know that this is either an amine or an amide because those are the only 2 options that will accommodate that nitrogen. The ester has the 2 oxygens, no nitrogen, and the ether is up here. It has an oxygen interrupting in the middle. So it is neither of those. The double bonded oxygen included with this nitrogen is telling me that I have an amide, not an amine. Amines only have nitrogen, no oxygens there. 47, which is an electrolyte. Electrolytes are aqueous acids, bases, or ionic things, so acids, bases, and salts. Hydrogen is covalent, or rather has covalent bonds. This is hexane, has covalent bonds. Glucose has covalent bonds. So does this acid, HCl, but because it's an acid, it breaks apart into ions. Water will go in and like whoosh, snatch it up and break it into H plus and Cl minus. And that is what makes it the electrolyte, is the mobile ions. So again, you're taking the definition and applying it to something. So in this case, it's acid, base, and salt just means something ionic. 48 is an acid-base indicator question. It says an indicator is added to an aqueous solution with a pH of 5.6. Which indicator is paired with its observed color in this situation? Oof, okay. So phenolphthalein, I'm going to rule that out right now because this is, if you did any acid-base labs, that's the easiest one. It's pink in a base and it's colorless in an acid. So that's not it because 5.6 obviously is an acidic pH. And then it comes down to everything else. So when it comes to reading these, I just want to help you out real quick. If we look at the entire pH scale going from 1 to 14, we'll put 7 in the middle. And we're going to do methyl orange for this example. So I'm going to put 3.1 right there, and I'll put 4.4 right here. The way you read this table is that it is red from 3.1 and down. So it'll be red until it hits 3.1, and it'll be yellow if it's 4.4 or higher. And then finally, it'll be orange in the middle. And it doesn't say orange on the reference table, and this is where like your knowledge of first grade art needs to come in. Really annoying that they do it this way. So if my pH is 5.6, which would be somewhere over here, then yes, methyl orange should be yellow. The same like concept applies for everything else. Bromthymal blue, or rather bromcrestal green, would be yellow only if the pH is 3.8 or lower. 5.6 is going to be blue because that's going to correspond to that 5.4. And then thymal blue will only be blue if the pH is greater than 9.6, and it'll be yellow if it's 8.1 or lower. I really dislike how they set up this acid-base table, the indicator table, but that's how they chose to do it, so that's how we have to choose to read it. That's that. All right, moving to 49 and 50, the final two multiple choice questions. Number 49 asks, solution A has a pH of 2 and solution B has a pH of 4. How many times greater is the hydronium ion concentration in solution A than the hydronium ion concentration in solution B? The pH scale is a log scale. So if you think of it like a number line, and if this is like a little confusing, I would suggest you go watch the pH video that's on this channel because I explain it in very good detail there. If you think all the way back to first grade and like the number line that was on your desk with your name written on it, each little jump on that number line was going to represent adding 1 or subtracting 1. On a log scale, each jump is going to be multiplying by 10 or dividing by 10. Now, the difference between 2 and 4 on the pH scale is a 10 and another 10 because it's 2 jumps. You have to go from 2 to 3 and then from 3 to 4. So that's why the concentration is going to be 4 times, not 4, it's 100 times. It's 100 times greater in the 2 than it is in the 4 because it's 2 jumps on the pH scale. And again, each jump is representing a 10-fold difference because it's a logarithmic scale. Also, hydronium, I probably should have said this. Hydronium is the H3O+. So really what this is it's the water that makes the solution plus that hydrogen ion. They just like get stuck together and they make hydronium, H3O+. This is also listed on table E as a poly. Oop. Right here, up at the top. So you have it right there. If you remember where to look for it, it's staring you right in the face. Then moving on to the final multiple choice, number 50. Which net change occurs in both nuclear fission and nuclear fusion reactions? Okay, fission and fusion are pretty much opposites. Fusion is when you have tiny little elements like hydrogens coming together to make helium. Fission is when you have something real big like a uranium, and then you'll hit it with a tiny little neutron, and then it's going to break apart into mid-weight elements like strontium and barium. So they're opposite. So we will not have small nuclei and large nuclei. That's not the same between them. What is the same is that we have a small amount of matter converted into a large amount of energy. I mean, if you think of the sun is just taking tiny little hydrogens and turning them into heliums, and then it's forming this big ol' energy. I mean, this energy moves 93 million miles plus. The sun's heat and light goes out very, 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 very far. Further than our brains can even, like, keep track of. Because it's so far. Okay. No questions so far, so we are going to move right along into part B2. This is where the multiple choice ends and the free response begins. Part B2 is definitely more straightforward than C. A lot of the time, there's not a lot of reading, and it almost seems like the questions are just, like, random. Okay, for 51, the two naturally occurring isotopes of lithium are lithium-6 and lithium-7. The table below shows the atomic mass and percent natural abundance for these isotopes. State the number of electrons in an atom of lithium-7. And you're like, how the heck am I supposed to know that? This doesn't even talk about electrons. Well, silly goose, lithium is lithium. It's an atom of lithium. This little 7 here is just telling you that the number of neutrons is different. The electrons are going to be the same. And because it is lithium with the atomic number of 3, it's still going to have 3 electrons. We're going to go check out the periodic table. I'm going to remind you. Okay, lithium's atomic number is right there. It's that bolded 3. It has 3 protons and it has 3 electrons, and that is what makes it a lithium atom. So that number there would be 3. Done. I have said it once. I will say it again and again and again. When it comes to these free response questions, do not write more than they ask for. Kids have a tendency to over-explain, and then you miss one tiny little word. Because you're getting to the end of the test, and you're tired and exhausted, and it's just, your brain is melting. And you wind up writing more than you need to, and you wind up getting it wrong. So keep your answers to the fill-ins as simple as you can. 52 asks to compare the energy of the electron in the first shell of a lithium atom to the energy of an electron in the second shell of the same atom. So lithium, we're saying we're comparing this electron to this electron, even though it has a second electron in there. The further away an electron is from the nucleus, the more energy it has. And that's because it's not restricted by the attraction of the nucleus, because it's further away. Think of magnets. Far away, less attraction. Boom. That's it. Sorry about that. The electron in shell 2 has more energy. Period. End of discussion. Stop writing. Keep it simple. 53 is the numerical setup for calculating the atomic mass of an element of lithium. This is really, like, at this point, you either know it or you don't. You take the atomic mass and you multiply it by the percent abundance. But percent is a number that you cannot just plug into a chemical formula, because 7.59 really means 7.59 out of 100. That's what it means. So translate that, it's really a decimal or it's really a fraction. So you would take the atomic mass 6.015, and it looks like there's 2 decimals in that number. 015, and you multiply that by the 7.59. There's 2 ways to do this, okay? Then you take that and you add it to the next isotope, 7.016 times its percent abundance, 92.41, but we have to divide the whole thing by 100. Or what you can do is preemptively divide it by 100. 6.015 times divide this by 100 is the same as moving the decimal 2 places. 0.0759. Add that to the next isotope. Its mass, 7.016 times the 92.41 divided by 100. 92.41. And that's it. You don't have to solve it. They're just looking for the setup. And that's all you would need there. Either of those 2 answers. They've been liking graphs on the more recent tests. The graph below represents the atomic radii of elements in period 3 on the periodic table of the elements. State the general trend for the atomic radius of the first 7 elements when considered in order from left to right. Sweet. It tells us. The graph says, hey, it's decreasing. The general trend. Atomic radius decreases. Boom. State in terms of valence electrons why aluminum and sulfur have different chemical properties. Literally has nothing to do with this graph. This is why the part B2s are annoying. They give you this graph and you think it's all about the graph, but it's not. It's not. They have a different number of valence electrons. That's why. Remember when I said that when in doubt, it's about valence electrons? This says in terms of valence electrons. So what I would do if I was like clueless, wait, I totally forgot. I'm so tired. This test is driving me crazy. Aluminum is right here. Sulfur is right here. Aluminum only has 3 valence electrons and sulfur has 6. They have a different number. That's it. The reason sulfur and oxygen have similar chemical properties is because they have the same number of valence electrons. Ooh, okay. Identify the element in period 3 that reacts with oxygen to form an ionic compound represented by X in the formula X2O. Love it. Okay, so we're talking period 3, and we're making an ionic compound with oxygen. Oxygen we know is a nonmetal, and an ionic compound has to be a metal and a nonmetal. The metals in period 3 are sodium, magnesium, and over here, aluminum. So like if I was stressed out and didn't really know what I was doing, I would crisscross all of them and figure out which one worked. So I would do sodium and oxygen, and that would give me Na2O. Magnesium and oxygen plus 2 and minus 2 would give me MgO. And then aluminum is plus 3 and oxygen is minus 2. And remember, these are the oxidation states. They're just coming from that top corner of the periodic table. I'd get aluminum 2O3, Al2O3. So which one matches? It's sodium. So the correct answer to 56 would just be sodium. Sodium or Na. Don't write both of them because one of the students out there is going to put sodium and then write Mg. And then it's like, we don't know what you're talking about. Which one was the, oopsie, that was a mistake. We don't know. Pick one of them. 57 and 58. Okay, lithium, beryllium, boron, and fluorine are 4 elements in period 2 on the periodic table. State in terms of electrons why the radius of beryllium plus 2 ion is smaller than the radius of beryllium atom. Do you see how irrelevant this is? They're also talking about lithium and fluorine, which have nothing to do with either of these two questions. Okay. 57. The trick for 57 is MELPS. Metals, electrons lose positive and smaller. When metals lose their electrons, they become positive ions with a smaller radius. And in terms of electrons, that is because beryllium now has an empty valence shell. So beryllium started out with a configuration of 2-2. And when it becomes a beryllium plus 2, it means that it gave those 2 electrons away and it only has 1 now. So the answer choices for this are going to be something like beryllium only has 2 electrons now. Beryllium gave away 2 electrons and now is smaller. Beryllium emptied the second energy level, which is what I would write. And that would be that. Draw a Lewis electron dot diagram for an atom of boron. Honestly, they're probably asking you this because beryllium and boron are near each other and their symbols are similar. Boron is up over here, the capital B, just B by itself. Its configuration is 2-3. So it has 3 valence electrons. The Lewis dot diagram only shows the valence electrons, and you draw them around the symbol. And when we draw them around the symbol, we have to kind of imagine that they are on the sides of an imaginary box. So that would be a correct answer. Again, just valence electrons as if they were on sides of an imaginary box. You cannot do it like this because you can only fit 2 electrons per side. You should not do it like this because, for real, these electrons are going to repel each other. When we're talking about the correct answer, it doesn't matter which side is the empty side, just that your electrons are not doubling up or even tripling up. Or that they're just like haphazardly drawn around, like a little halo. We don't do that either. Although, potentially somebody would count that if it was like super close together and kind of like curvy. I wouldn't count it. It depends on who's scoring. Keep them far from each other. That's the best practice. Okay, for number 59. An incomplete equation below represents a reaction between 2-butene and hydrogen in the presence of a catalyst producing one compound X. We don't know what it is. Explain in terms of molecular formulas and structural formulas why 1-butene is an isomer of 2-butene. Okay. Isomers mean that they are made of the same stuff but constructed differently. And they're asking you specifically to talk about molecular formula and structural formula. So I would write they have the same molecular formula. But they have a different structural formula. They're built differently. And that would be it. The thing that I just said verbally, they have the same chemical formula but are built differently, I would accept that on the test. But when it comes to those explained in terms of, I like to use those exact words in my answer so that there is absolutely no confusion that I answered the question properly. So that's my recommendation. When it says explain in terms of blank, Literally use those words in your answer. Okay, and then this is asking to draw a structural formula for the missing product X. An incomplete equation below. Okay, so this would be the addition reaction. Give us some space here. I'm gonna draw it like up here, even though I had been using the answer booklet, but I don't want to. Here we have 4 carbons. I'm going to continue with those 4 carbons because there's no indication that we're breaking this apart. What we're doing is adding this hydrogen across the double bond. So what's going to happen is that the double bond is going to be reduced, meaning that it gets broken down to a single bond. And then this carbon and this carbon, carbon 2 and 3, are now open to accept the 2 hydrogens coming from that hydrogen molecule. So I'm going to put my H's around because the H's have now taken the place of that double bond. And that would be it. And they're specifically saying to draw a structural formula. You can't name it. And I wouldn't name it because that is butane. But if you wrote butene, you're going to get marked wrong. If you wrote butine, if you wrote propane, because your brain's melting, because you get into question 60 on this test, only do what they ask. If they ask for a drawing, just draw it and kiss it goodbye. So you should have gotten the butane for that. Next up is a bunch on acid-base. In a titration using a pH meter, 16 milliliters of 0.18 molar sodium hydroxide exactly neutralizes a 24 milliliter sample of hydrochloric acid in a flask. During this lab activity, appropriate safety, blah, blah, blah. Okay, 61. State the number of significant figures used to express the volume of the hydrochloric acid. Oh boy. Okay. The volume of hydrochloric acid is this 24 milliliters. They don't say, hey, this is the volume of it. They give you the milliliters and they expect you to know that that is a volume measurement. And we have 24.0. When it comes to significant figures, I'm looking at whether my decimal is actually written. Is the decimal present or is it absent? If the decimal is present, I'm going to approach the number from the Pacific side. I'm looking for the first non-zero number, which is 2. I'm going to count the 2 and everything that comes after it, no matter what. So in this case of 24 with a decimal, I have 3 significant figures. If you need help with those, there are at least 2 videos on the channel about counting sig figs. It's probably at most going to be 1 question, so I wouldn't stress about it. 62. Identify the negative ion in the sodium hydroxide that is used in the titration. Even if you didn't know that this was a base, sodium is a positive ion, and then hydroxide, it's on table E. That's the negative ion. I'm going to show it to you on table E. It is right here, hydroxide. And that's the ion. It's OH with a minus. Even though they don't write the 1, it's really -1, not just minus. Chemists are lazy. They don't write it because they say minus and -1 are the same thing. Because they're annoying. Says the chemist. 63. Getting ahead of myself. Compare the number of moles of hydronium ions in to the number of moles of hydroxide ions in the titration mixture when the HCl is exactly neutralized by the NaOH. Your brain might be telling you to do some math here because we're talking about numbers of moles, but the key here is that your solution has been exactly neutralized. Wow, what on earth? Our solution has been exactly neutralized. That's the big point here. So that means that the H plus has to be equal to the OH minus, right? Because that together, HOH, is water, and water is neutral. The acid-base way to write water, H2O. So they would just have to be equal. So the number of moles are going to be equal or the same, and that's all. There is no reason to try to determine it because they didn't ask you what is the number. They said to compare. And a comparison is like greater than, equal than, or the same when it comes to numbers. Okay. Complete the equation in your answer booklet for the neutralization reaction by writing the formula for each product. So I don't have the answer booklet open. I know the link is in the description. I'm just going to pretend that I'm looking at it. So we know at this point that the order of the reactants doesn't matter, right? If the booklet has the sodium hydroxide first and the hydrochloric second, that's fine. It really does not matter. This is a neutralization reaction, so we should know that we're getting some type of ionic salt and we're getting water. It's a double replacement reaction, so we're going to take this H and pair it up with the OH, giving us HOH or H2O. Those are both, they're equivalent to each other, so they're correct. And then the salt, in this case, happens to be table salt, which is sodium chloride, NaCl. That really could go either way. You could put the NaCl first and the HOH second. Sometimes you'll have something like K2S because you had potassium hydroxide and hydrosulfuric acid. The combinations are endless. This is a 1-to-1 to 1-to-1, so there's no need to balance this. My assumption is that they wouldn't have you balance this just because you have to determine the products and balance, and I feel like that would be a 2-point question, but on the chem test, every question is worth 1 point. So it would be something probably simple. Okay, then 65. Determine the molarity of the hydrochloric acid sample in the titration data. And for this, we would want to use the titration formula. And anytime we do math, we go to the back cover. And we're looking here at the titration. We have the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. So we're going to use our data here. There's our base data. The molarity of the acid is what we're looking for. We're going to multiply that by the volume of the acid, the 24 milliliters from up top. That's going to be equal to the molarity of the base, 0.18. We're going to multiply that by the 16 milliliters for the volume. .18 times 16 is 2.88. That's equal to 24 m. Divide both sides by 24 in order to get m by itself. And the answer I am getting for the acid specifically, the molarity there is 0.112 molar, which to me makes sense. This is a 1-to-1, meaning that for every hydrochloric acid that breaks apart, you get 1 hydrogen. And for every, sodium hydroxide, you get 1 hydroxide. So it is a 1-to-1 if we were looking at the little baby subscripts. That wasn't important for this question, but for some other questions, it may become important. So if you had like a diprotic acid, you would put a 2 on the acid side. If you had like calcium hydroxide where it was CaOH2, you'd put a 2 on the base side. So just be mindful of that when you do the titrations. All right, if there's no questions, I'm going to keep moving. We only have 20 questions left. And here we come to part C, where they get way more annoying. Again, this is why I like to do the test backwards. I do all the annoying stuff first, and then the last question that I answer is really the first. It's like, what's the charge of a proton? You're like, oh, thank goodness this test is over. Okay. An average person aboard the International Space Station requires 840 grams of oxygen per day. To produce the oxygen needed, water undergoes an electrolysis reaction. The oxygen produced is vented into the cabin, and the hydrogen is vented into outer space. Interesting. Hydrogen is, like, not littering in outer space, I guess, but it's kind of, like, flammable. So I wouldn't want that, like, right outside where I was living, but okay. The reaction is represented by the balance equation below. Some gases in the International Space Station must be removed from the air in order for astronauts to breathe. Carbon dioxide can be removed by using solid lithium hydroxide. Show a numerical setup for calculating the number of moles of oxygen gas required for the average person per day. Ooh, and it tells you the gram formula mass, or the molar mass of oxygen, is 32 grams per mole. So there's like a bunch of ways that you can set this up. I always take the given and like set it up as a question. So 840 grams is equal to, I don't know how many moles, so I'm going to label it X. But I do know that 32 grams of oxygen is equal to 1 mole. And that would be a correct numerical setup. You also could use this setup here where it says mole calculations. Let's just slide this over. So the number of moles is equal to the given mass divided by the formula mass. So you could just put X moles. Let's kind of like divide this. X moles is equal to the given mass of 840 divided by the 32. That's also equivalent. Anything that's mathematically equivalent to either of those two setups would work as well. Okay. 67. Ooh, I love oxidation numbers. State the change in oxidation number for oxygen during the electrolysis reaction represented by the equation. Ugh, love it. Okay. Oxidation numbers. For elements that are not bonded to anything, their oxidation number is 0. And in this case, we have oxygen in a bond. Oxygen in a bond has to be -2. It's the only option. Oxygen is either -2 because it's bonded to something, or it is 0 because it's the element in its natural state. So this is oxygen, the element. Even though it's diatomic, it's still 0. And that's because that's its natural state. That's the way nature made oxygen. So the oxidation state, it changes. State the change. So it goes from -2 to 0. And that would be the answer. That was a lot less exciting than I thought it would be. I like when you have to like do the math for it. I have a video on that if you need help with that. Determine the number of moles of oxygen vented into the cabin when 120 moles of water undergoes electrolysis. Ooh, okay, so this is the mole ratio. If we look at the balanced equation, which they very nicely told us was a balanced equation, which is why you want to read these things even though your brain is melted, I know. The mole ratio, we are looking at water and oxygen. And they are currently in a 2-to-1 ratio. So I set this up kind of like this. Hydrogen, or water rather, is 2 moles. If I use 2 moles of water, I'm going to get 1 mole of oxygen. If I have 120 moles of hydrogen, I would have X moles of oxygen. And that's how I set that up. So then you cross multiply, because you have 2 fractions equal to each other with 1 variable or 1 unknown. So this would be 2x is equal to 120. Divide both sides by 2, and x is equal to 60 moles of oxygen. Some of us that are math brained just look at that and go, duh, 2 and 120 is the same as 1 and 60. Others, like me, don't think like that, so we have to kind of solve it. But 60 moles of oxygen would be the correct answer. 69, determine the percent composition by mass of hydrogen in water. Sweet. Okay. Percent composition by mass. I like to do, I've always called it a QMT chart, where I find the molar mass, or rather the gram formula mass. So it would be like, I have a hydrogen and an oxygen, and then I do QMT, quantity, mass, and total. And for water, it's kind of silly to do it because it's such an easy one. Quantity is counting. I have 2 hydrogens and 1 oxygen. Mass, you're going to pull from the periodic table. Mass of a hydrogen is 1.008. Mass of an oxygen is 16 even. You multiply going across. 2 times 1 is 2. The total of all of my hydrogens is 2. 1 times 16 is 16. All of my oxygens, all one of them, has a mass of 16. And then you would add that going down to find out the total mass. So the water has a mass of 18, but hydrogen has a mass of 2. And this QMT chart works especially well when you're working with hydrates, because you get like everything listed out in a beautiful table. So for the percent composition, I'm going to do hydrogen over water. So that would be 2 over 18, and because it's a percent, I got to multiply it by 100. 2 out of 18 is going to give me 11%. It's 11.11. Now, when it comes to what's going to be the correct answer, when it comes to things like this that have to do with rounding, there is going to be a range in the answer key. And I think the answer key is in the description of the stream. It should be anyway. There's going to be a range. So it's going to say like from 10.8% to 11.4%. And if your answer falls in there, you'll be fine. So it's 11.11 if you round everything to the whole number. Otherwise, it would be 1.016 out of 18.016. That doesn't make sense. 2.016. There we go. Times 100. Okay, so if you pull like the numbers directly from the periodic table and you don't round to the whole number, you're going to get 11.19. So that's why there's a range, because different kids are going to pull the data a little bit differently. Question 70. Balance the equation for the reaction between lithium hydroxide and carbon dioxide in your answer booklet using the smallest whole number coefficients. I don't know what the product of this reaction is. Lithium hydroxide and carbon dioxide. Is it lithium carbonate and water? Let's see. I'm gonna go get the answer booklet. June 22. Answer booklet. And we're on question 70. Oh, guess who was right? Take a look at that. Okay, we are going to get Li2CO3 and water. Okay, when it comes to balancing, what I like to do is do this and split my reaction into a before and after. and line up all my elements. So here I'm working with lithium, I am working with oxygen and hydrogen, and then carbon. Now, here's the thing. The oxygen is split, right? We have some oxygens in the lithium hydroxide and some oxygens in the carbon dioxide. So it's kind of, a lot of the time what I like to do is when I have a poly, I like to hold it together, but I don't know if that lithium hydroxide is breaking apart. Like, I don't know if the O is separating from the H and the poly is breaking, or if they're staying together and water is HOH. So because I'm unsure, I'm going to leave them together. On this side, I have one lithium, not one oxygen, I have three. One in the lithium hydroxide and two in the carbon dioxide. I have one hydrogen and one carbon. On the product side, I have two lithiums, one carbon, two hydrogens, and 4 oxygens. And because their oxygens are all over the place, I'm going to save those for last. A lot of the time, they wind up fixing themselves as we go. Okay, so I'm going to put a 2 out in front of the lithium hydroxide. That'll change my lithiums to a 2. The hydrogens will also be a 2. Sweet, those got fixed. And, oh, would you look at that? This 2 is going to give me 2 oxygens over here, plus I have 2 right there, and that gives me 4. So I only have to put a 2 in front of the lithium hydroxide for this reaction. Beautiful. All right, let's keep going. One sample of tap water contains dissolved ions such as calcium and magnesium and carbonate. A 150-gram sample of this tap water contains 0.00075 grams of calcium carbonate. When the ions in the tap water are present in greater concentrations, the water is called hard water. Hard water can damage water pipes and water heaters by producing large deposits of solid calcium carbonate, known as scale. Ooh. Some homeowners have a water softener to replace positive ions, such as calcium and magnesium in hard water, with sodium ions. Determine the parts per million of the calcium carbonate in the tap water sample. Weird. Okay. What is the size of the sample? Okay, the total size of the sample is 150 grams. And the tap water has a very small amount of the calcium carbonate. And I want to do the parts per million. So we will do this and check out parts per million, which is this right here, concentration. We want the mass of the solute divided by the mass of the solution, which, spoiler alert, is the whole thing. I shouldn't have said spoiler alert because it's not what we're doing. It's the whole thing. So we are going to take the 0.00075 and divide that by the 150 plus that amount. Ooh, no, we're not. 150 is the entire sample. Okay, so that is included in the 150. Okay, that's the whole solution. Sometimes you have to add them, so just be mindful of that being a possibility. And then we are going to multiply that by 1,000,000, and 1,000,000 has 6 zeros, and if it doesn't, then you need to hire an accountant that you trust. 0.00075 divided by 150 times 1,000,000. 1, 2, 3, 4, 5, 6. Those were all zeros, and I'm getting whole number 5. So that would be 5 parts per million. Next up, state in terms of aqueous ions why this tap water can conduct an electrical current. Okay, specifically, you must talk about aqueous ions. Aqueous ions means that we have dissolved ions in the solution. Dissolved ions can conduct electricity. That is the definition of an electrolyte. So if the ions are dissolved or if they're mobile, they can conduct electricity. Using the key in your answer booklet, draw at least 2 water molecules in the box, showing the orientation of each water molecule towards the calcium +2 ion. Interesting. Can I just do a little screenshot of this? And can I paste it? Ooh, I can. Look at that. Okay, so this is what we're going to use right here, just because I don't feel like pulling the entire answer key into Cami. Come on. Oh my goodness. Does anybody else hate Cami? Or is it just me? Ay, ay, ay. Okay, so we are going to make sure I'm not leaving out anybody's questions. I'm going to pull up. Ay, 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 ay. There we go. Okay. We're going to draw these water molecules on the... Oh boy, give me this. So calcium is a positive ion. And water molecules are this like little Mickey Mouse shape, right? In a water molecule, the hydrogens are the positives and the oxygen, which is the big one here, is the negative. So it would look like this, and you have to draw at least 2 of them. I would only draw 2 of them. And that would be that. So if we were to look at a water molecule, let's look at the Lewis structure just for a quick second. This is that big atom, and the hydrogens are the 2 little ones. This is the partial negative, and this is the partial positive, and they just want you to point out that the calcium is going to attract the oxygen side of the molecule. Okay, moving right along. A 3% hydrogen peroxide solution, H2O2, is commonly used as a disinfectant. Hydrogen peroxide decomposes as represented by the balanced equation below. State the evidence from the equation that the reaction is exothermic. Sweet, I love these. You know why? Because they like flat out tell you. Exothermic means that heat is exiting. So heat is released, heat exits the reaction, heat is a product. One of those will work. It just flat out tells you. Conversely, endothermic reactions, heat is entering. For question 75, explain in terms of substances why the reaction is a decomposition reaction. I would say that the hydrogen peroxide breaks down into smaller pieces. Smaller substances, because they want me to use the term substances. And let's imagine that I wrote this nicely. H2O2 breaks down into simpler substances, and that is what makes it a decomposition reaction. That is what a decomp is. A synthesis would be the reverse. State how increasing the temperature of the H2O2 affects the rate of the reaction. It is going to speed up the reaction. They just want to state how it affects the reaction, not why. So don't explain why. The real reason is because the hydrogen is going to be driven off, is what we would say. It evaporates into the air. It's exothermic, so adding a bunch of heat is going to like expedite the reaction, that type of thing. So yeah, our rate is going to increase on that. For 77, it's saying to draw on the diagram. So I'm going to pull that snipping tool over again, grab a screenshot. And we will paste that right there. Okay, there we go. Draw a double-headed arrow to indicate the interval that represents the heat of reaction. Heat of reaction is the difference between the products and the reactants. It is this space right here. That is delta H. It did not ask you to label it, so I wouldn't, just in case you labeled it wrong. So that double-sided arrow, again, is the difference between the reactants and the products. Do not mark up anything on this table aside from that double-sided arrow. Just give them what they ask for. Don't decorate it. Keep it simple. This, again, is an exothermic reaction. We know this because this is losing energy over time. The delta H would be negative because in order to calculate delta H, we do the products minus the reactants. Products are obviously a lower number than reactants. Everybody's favorite Voltaic cell question, which I like the Voltaic cells. Call me crazy. During a lab activity, appropriate safety stuff, blah, blah, blah. A student constructs a Voltaic cell with magnesium and copper electrodes. The diagram and net ionic equation below represent this cell and the reaction that occurs. Oh, I love when they do this. Everybody freaks out at the Voltaic cell, but then they ask you a question. And part of the reason people freak out is just because it's always at the end. It's really hard to remember, but then they like throw you this bone, but you're so exhausted that you may not even realize that it's a simple question. Identify the subatomic particles that flow through the wire as the cell operates. Subatomic particle means that your answer has to be proton, neutron, or electron. That's it. Then, at this point in the school year, you should know that protons and neutrons don't just like casually migrate out of atoms. They only do that if it's a nuclear situation. So that leaves you with just electron to be the answer choice. And that's all. That's the whole answer. Again, keep it simple. Don't over-explain. Give them exactly what they want. 79 says compare the number of electrons lost to the number of electrons gained during the reaction in the operating cell. This may seem like it's a hard question and maybe there's some math involved, but I promise you there's not. When it comes to comparing numbers, the numbers are either greater than, one is greater than the other, one is less than the other, or the two are equal to each other. Those are the only options for comparing numbers. So again, it's kind of like a multiple choice question, but the multiple choices are in your brain. They're not written down on the paper. You know that the very first law of thermodynamics is called the law of conservation. Matter cannot be created or destroyed. Charge cannot be created or destroyed. Energy cannot be created or destroyed. The number of electrons lost has to be equal to the number of electrons gained simply because the law of conservation said so. Isn't this your favorite Voltaic cell question ever? Question 80, state the form of energy that is converted to electrical energy in the operating cell. It's chemical energy. It's the chemical energy that is stored within the bonds of whatever the magnesium is bonded to, whatever magnesium solution this is, and same with the copper. It's all within the substance itself. So that is chemical energy converting to electrical as the battery operates. Okay, now we're going to be annoyed. Write a balanced equation for the half reaction that occurs in the copper half cell when the cell operates. This one's not so bad because it's giving you like 90% of the half reaction here. We're starting out with this copper and it's turning into this version of copper. And then all we have to do is balance it. So we have copper with a +2 turning into a copper with no charge. And no charge means it's a 0. It's a copper atom. If it's an atom, it has no charge. We need to only use electrons in order to balance this. And when that happens, that means that I will be putting 2 electrons over here because this is 2 negatives and +2 is going to equal out and give us 0, which will be equal to the products which have a charge of 0. Also, it's the one that's being reduced, if that is something that helps you. If we check out the reference table, table J is maybe like the best table, but also possibly the worst table. It's kind of hard to judge. Table J is going to put the anodes up at the top and the cathodes down at the bottom. And we, in this case, would be comparing magnesium and copper. So when we look at those two together, magnesium is going to be the anode in this situation, and the anode is going to undergo oxidation, while the lower one, the cathode, is going to undergo reduction. So reduction is, Leo says, GER, or oil rig. Reduction is gaining electrons. Gaining electrons would have to be a reactant. Ooh, okay, and now 82. Identify one metal from table J that is more easily oxidized than magnesium, which is what we were just doing. These are all of the answer choices. Everything higher than magnesium is an acceptable answer choice. Lithium, rubidium, potassium, cesium, barium, strontium, calcium, and sodium. Because the anodes go to the top, they love to be oxidized, the cathodes at the bottom, which love to be reduced. So like this maybe was the best set of Voltaic cell questions ever. I'm just going to put lithium. I like lithium. Last set. Fantastic. Element 117, which currently has a name, but they're calling it in the Regents Exam, UUS, has been synthesized and has at least two isotopes, UUS-293 and UUS-294. Atoms of UUS-293 can be made by bombarding berkelium-249 with calcium-48 in a reaction represented by the nuclear equation below. The berkelium-249 has a half-life of 320 days, decays by beta emission, and also emits gamma rays. Determine the fraction of berkelium-249 that remains unchanged after 960 days. All right. I'm going to do this down here. I love half-life questions. It's just like my personality, I guess. Up top, we're doing fractions, and below, we are doing time. And that time is going to be measured in days. So my fraction originally is going to start out as 1/1, and today's date is 0. And after my first half-life, 320 days will have passed, and I will only have half of my sample left. I'm going to cut my sample in half again, and I'll be down to 1/4. The 320 is going to be added again, so I will add another 320 because it's the same half-life happening each time. So at this point, I'm up to 640 days. My fraction will be cut in half again. I'll come down to 1/8. And at that point, I'm adding the half-life, 320 days. I will be up to the 960 days that the question is asking about. So the fraction that remains is 1/8. Again, an entire video on how I do these half-lives in the setup, if that's something that you need or you're interested in. But I think this like horizontal table is the best way to do it. Okay, 84. State in terms of both protons and neutrons. So you have to talk about both of them in the answer. Why UUS-293 and 294 are isotopes of the same element. And I would not even talk about numbers. Like, I wouldn't actually put in digits. They have the same number of protons. That's what makes them the same element, but they have different mass numbers because they have different number of neutrons. That's all they're looking for. Don't overdo it. Okay, finally, the last question. Hip, hip, hooray. Complete the nuclear equation in your answer booklet for the alpha decay of UUS-294 by writing a notation for the missing product. Okay, so I'm just going to transcribe it because that's going to be quicker than trying to copy and paste it. So we have 294 and 117 with the symbol UUS. And it is showing alpha decay, HE plus, and then we have the blank. So the way that I like to do this is kind of like treating it like algebra, because that's the way that it works. I do the top and the bottom. 294 is equal to, yields is chemistry for equal, and I'm only doing the top digits right now. So this would be 4 plus a mystery number. That mystery number would have to be 290. And then across the bottom, I have 117 is equal to 2 plus some imaginary number. Let's make it z, because y is actually an element. So that would have to be 115. And then I have to go look up the periodic table, what number 115 is, which I believe is UUP, but I'm still going to go look it up because I'm not sold on that being the answer. Yes, I am right. These elements all got names. UUP is for 115, like un pent. That's how they came up with it, until it was verified and then it got a name. So the symbol there would be UUP because the atomic number is 115. And that is the entirety of the June 2022 test. We've been streaming 2 hours and 10 minutes, which is fantastic. I think this was my fastest test so far. So if you need a little bit more details of going through absolutely everything, go check out one of the other streams. I am doing one tomorrow. It should be around 2 o'clock if all goes according to plan. There is a reference table stream, which was about 2 hours I did earlier this week, which I think would like rock your socks. It's going to like really take you to the next level if you're feeling iffy. If you are like last minute studying, I would watch the reference table video and then I would review vocabulary terms and leave it at that. It's very easy to become overwhelmed because it's 85 questions and you can only do so much before your brain melts. So please make sure to subscribe so that you don't miss tomorrow's stream. If you have any questions, feel free to leave them in the comments. I will try to get back to as many of them as I can. And then all over this channel, there's a bunch of videos like specifically on these topics. So if there's something that you're like, ugh, I don't remember half-lives all that well, everything should be like around a 10-minute video to like really help you figure out what you need. Okay, that's it. I will see you tomorrow. Have a good one.